lambda Ginsburg model here flows to a particular point in modern space of CFT, not just any.
It depends on this parameter t here. You can specify it. Yeah.
That's,
Okay, so compute the two-step partition functions. So using this exact formula what I presented earlier in this talk, we can compute the two-step partition function of this gauge linear sigma model, which is given by this expression. And using this identity between the Bessel function and the ratio of the gamma function, one can easily rewrite this expression into the following form, which can be also rewritten as the following form, which is nothing but the two-step partition function of the lambda Ginsburg theories, whose twisted superpotential exactly agrees with this expression.
so sorry, well, what was tau in the gauge linear sigma description?
Fi prime is less than the two-dimensional set time. So
It was the, oh, okay.
the Keller model.
The Keller model.
Yes. This one. So this result can be understood as some kind of additional verification of this Fourier-Farfan mirror map from this two-step partition function point of view.
This is just really trying to understand the setup. If
Yeah.
you care about, and I guess here you don't care about the Keller model on the Ginsburg model side, but this will flow to some particular point in the Keller model space from this point of view, but you don't keep track of that information.
Any other questions? All right. So let's now add to the theory the following on a certain superpotential terms. And this gauge linear sigma model with the superpotential W will describe certain compact Calabi-Yau manifold, which is more precisely, which is known as the complete intersection of the toric varieties. But if you use this Fourier-Farfan mirror map, it seems that the Landau Ginsburg description mirrored to this gauge linear sigma model with superpotential W seems to be, how can I say, is unaffected by this superpotential W. More precisely, this twisted superpotential W in this mirror Landau Ginsburg description is not modified at all, even after you introduce the superpotential W in the gauge linear sigma model. Nevertheless, we believe that there must be some difference between these two Landau Ginsburg theory mirrored to the supersymmetric gauge theory without superpotential and with superpotentials. And it turns out that there are subtleties in choosing the fundamental variable to describe the Landau Ginsburg theory, which are mirrored to this gauge linear sigma model with the superpotential W. And in order to solve these subtleties, people need to carefully look at the target space geometries. In other words, we need some knowledge about this target space geometries beyond this gauge theory data, in some sense.
You mean changing the what you call fundamental fields in the Landau Ginsburg model changes what the CFT flows to, and modern space also different?
Mm-hmm.
Is there some simple relation between them, or
Simple relation between what?
between the moduli spaces of this Landau Ginsburg model for these?
Oh, no, it doesn't depend. This choice doesn't depend on this modular space.
It doesn't affect.
Yeah. And as I will show you in a second, this two-step partition function can resolve the subtleties automatically without, without relying on this target space geometry knowledge.
I didn't understand what you mean by choosing the fundamental value.
It will be clear when you look at the next slide. So let's compute the two-step partition function of these gauge theories. So first I want to remind you that in order to introduce the superpotential on the two spheres, there's one condition we need to satisfy, which is the superpotential U1R charge must be given by 2. That implies that some of the chiral multiplets in this gauge theory should carry some non-zero U1R charge. So let me denote that U1R charge as a QA. So some of them is non-zero. And then using this exact formula, we can easily compute the two-sphere partition function of this gauge linear sigma model with superpotential, which is given by these expressions. And you can see this explicit, QA dependence here explicitly, explicit dependence of this QA. Then using this identity between the Bessel function and the ratio of the gamma function, you can rewrite these expressions into the following form, which is almost the same as what we obtained for the two-square partition function of the Landau-Ginzburg theory mirror to the gate in the sigma model without superpotential, but except these extra factors in the measures. And
so clearly the CFT you're talking about here has non-compact target space.
But in this case, when you introduce superpotential, then this, it is for the compact Calabi-Yau. So this extra factor arises only when you consider this non-compact Calabi-Yau. And from these extra measures in the extra factors in the measure, we can determine the right variable to describe the Landau-Ginzburg theory, which is given by this expression.
But what we're saying here is that there's a non-compact. There's another CFT with non-compact target space, but same moduli space as the one with non-compact target space.
Yeah. The Kähler moduli is the same.
So from the point of view of the effective low-dimensional theory, the logic that chooses the right variable is the variable in which the kinetic term is constant. I mean, otherwise, variable redefinitions you can always do in quantum field theory. But it sounds like near x equals 0, there's something you can introduce a singularity.
Yes.
So the question of which variable is the kinetic term?
Yeah. Thank you. And this variable chosen by this two-square partition function perfectly agrees with the known prescription in the literature how to choose this Landau-Ginzburg variable due to this gating and sigma model with superpotential. So this is very nice, but we want to do something new. And we found that this conventional method to construct the mirror descriptions cannot extend to the larger class of the gate theories in the 2 dimensions, such as the non-abelian gate in the sigma models, which can describe a certain Calabi-Yau manifold beyond the toric varieties. For instance, let's consider the simplest example, the UN gate theory coupled to some chiral multiplet in any representation R, and then we can add some arbitrary superpotential to this theory. This theory sometimes can describe a certain manifold, which is known as the complete intersection in the Grassmannian manifold, rather than toric varieties. Unfortunately, the mirror description of this manifold is not clear at all at the moment. But still, we can compute the exact two-square partition function of this 2-dimensional non-abelian gate in the sigma model using this exact formulas. We obtain some expressions, integral representations, and then using this identity, what I repeatedly use, this one, the identity between the vector function and the gamma function, we can rewrite that expression into the following conducive form, which is almost the same as the two-square partition function of the Landau-Ginzburg theories, where the twisted superpotential W is given by these expressions, and we have an extra factors here, which is more or less the fundamental determinant. And these expressions perfectly agrees with what Hori and Baffa has conjectured for the mirror description of this particular non-abelian gate in the sigma models.
So for this discussion, is there any reason to restrict to the Calabi-Yau 3 code as opposed to other dimensions?
You can generalize to any dimension.
There's no difference, right?
Yeah, no difference ever.
And how general is the class of Calabi-Yau manifold described by non-abelian engineer model?
It is not answered yet.
So actually, so this is crucial to use this on the previous slide, this Fourier transform of the Bessel functions, right? And in some sense, that's already assumed the abelian duality is at
Kind
work,
of, yeah.
in some sense. So I'm just curious. Then you begin with some non-abelian GLSM, and then you basically use this abelian identity to rewrite this Landau-Ginzburg. So of course you get something like Landau-Ginzburg. I mean, does it actually prove anything? I guess that's my question.
I didn't say that I prove anything.
Yeah, I'm just curious. It's
I just
really
said
extended.
that
In some sense, it's like you kind of adopted the Hori-Baffa recipe, and just then you basically just get what you expected to get. But is there actually some other independent way to verify? I guess that's the question. Is there some other independent way to verify this is really the?
I think this is this is one way to see this this proposal from the two-square partition function's point of view. So I think you're asking about whether there's another way to understand.
Yeah, to understand why this has to be right, or because right now it's like
I don't have any definite.
If you feed something to a sausage machine, you get something from sausage house. Yeah.
So transportation.
Yeah.
Yeah. No, I don't have. Yeah.
No. So even mathematicians have nothing to say, like from your experience.
Well, I don't know actually. I mean, this is just a mathematical identity.
Yeah, I understand. So, but
Yeah.
they have nothing to say about the mirror deal about.
Well, I mean, this expression, when you remember this result, then you can read up this data for the Landau-Ginsburg theory from this expression.
Well, anyway.
Are there some examples of Calabi-Yau manifolds that are known to not admit non-abelian GLSM description?
Do not admit
Yeah.
non-abelian. This complete intersection of torify.
No. The ones that do, I asked for ones that do not admit such.
The gauge linear sigma of the description.
Yes. For example, does
I think
non-algebraic
there must be
K3
some, there must be some,
does non-algebraic K3 have the engineering description?
K3.
Non-algebraic K3.
I don't think. I don't know. But I think algebraic case, yes. There's
Algebraic K3, of
you know,
course.
yeah.
But, yeah.
No, I don't, yeah. Sorry, I don't know the answer.
I'm just thinking in analogy with the
Mhm.
n equals 4 case.
N equals 4 in
2D case. I mean, there are plenty of hyperkähler manifolds that are, if you want to describe as hyperkähler quotient, has to be infinite dimensional hyperkähler quotients. So I'm just wondering whether you may need to extend to infinite rank gauge groups in order to describe certain class of other manifolds.
I see. I didn't thought about it. Okay. Any other questions? Okay. So let me now move on to other applications, which is the phase of the gauge in your sigma models. So for simplicity, let me focus on this example: the U1 gauge theory coupled to NF chiral multiplet electric charge plus 1, NF chiral multiplet electric charge minus 1. We also introduced F5 parameters in the two-dimensional theta angle to these theories. Then by solving the vacuum equations, one can easily show that, at least classically, there are vacuum moduli space, which is known as the Higgs branch vacuum moduli space, when Fi parameter is non-zero. But when Fi parameter is 0, there is an additional vacuum moduli space, which is the Coulomb branch moduli space of this gauge theories. So that implies that, classically, the low energy effective theories living in this Higgs branch with negative Fi parameter cannot be analytically continued to the low energy effective theories in Higgs branch with positive Fi parameters. This is because somewhere between we have an extra massless state, so this description cannot be, this effective description will be broken when you approach this line Fi parameter equals to 0. However, when you consider some quantum correction, this picture is not the case. What people found is that the low energy effective theories with negative Fi parameter here can be analytically continued to the physics with positive Fi parameters unless the theta angle is set to 0 due to the quantum corrections. And actually, so only when this Fi parameter C and theta angle, both of them are set to 0, then we have a additional massless mode, which can describe the Coulomb branch moduli space. The Coulomb branch moduli space can arise only at this point here. So this is the quantum phase of the gauge linear sigma modulus, which was discovered by this Witten in early 90s. So I think it would be interesting to investigate this fact from the two-scale partition function point of view. Okay, so using this exact formula, we can compute this two-scale partition function of this U1 gauge theories, which is given by this expression. A little complicated. Here, M and M tilde are twisted mass term for this chiral multiplet, plus 1 charge and minus 1 charge. So we have some expressions, and we can massage them to be massage them into the following form, which involve this finite sum, and the sum n can be expressed in, as a product of the holomorphic functions times its complex conjugate. And this expression is actually very interesting because this finite sum can be understood as a sum of the isolated vacuum, which can be identified as a Higgs branch root. And this holomorphic piece in this domain can be identified as a vortex partition function, which is the two-dimensional analog of the four-dimensional Nekrasov partition function. Here, this function f is nothing but this hypergeometric functions with this degree, and this parameter c, c can be is given by this is defined by e to the 2 pi tau, where tau is this complex phi and phi parameters. So some of you may wonder why this two-sphere partition function can be expressed in terms of this vortex partition function times anti-vortex partition functions. And this question was answered by this Benjamin and Cremonesi, and they found that there is a certain two-exact deformations, so that this path integral can be localized onto different supersymmetric set of point configurations, which is nothing but the vortex instanton configuration localized at the north pole, and the anti-vortex configuration localized at the south pole. And that explains why these two-sphere partition functions can be written as it is written in terms of the vortex partition function times its complex conjugate. But anyway, the thing I want to stress at this point is that from the analytic structure of this hypergeometric functions, we can easily study this analytic structure of this two-sphere partition function as well. And one can show that this two-sphere partition function with negative Fi parameter can be analytically continued to the two-sphere partition function with positive Fi parameters, unless the theta angle here is not set to 0. Furthermore, we can show that this two-sphere partition function becomes singular exactly where this Fi parameter c and the two-dimensional theta, both of them are set to 0, which is consistent to what Witten discovered in the early 90s. And there are some people like David Morrison and his company who use this fact to analyze the quantum phase of this non-abelian gauge theory in the two dimension, which still remains a challenge.
There's a relation between z and tau here.
Where's the z?
Z in the form of z and f of z. The argument, I mean,
Sorry.
What is z is the question.
fp of z, the
Z is this one. Sorry, I made a mistake.
Okay.
Yeah, cool. Sorry. Typo.
And where does tau appear there?
Tau here.
z,
Oh,
z is
it's
key.
Z. Right. Okay. So I think I need to stop here. I mean, because I don't think it's not good idea to give you more more information in a single talk. So this is the thing what I want to talk in this morning talk. In the afternoon, I will discuss about the other application of this two-sphere partition function, which is this the Walsh instanton to complete the Walsh instanton correction to the jamological metric. Then I will introduce to you about some issues about the Ramon charges of the D-branes in the orientable plane. Then using this another exact result in two dimensions, such as hemisphere partition functions and RPT partition function, I will solve this puzzle, and I will finish I will summarize the talk. So this is all I want to say today, and thank you very much.
Are there questions or comments?
So the elliptic genus is independent of your Z, right?
How? Yes, it's independent of how.
Well, this is a
Sometimes you need to be very careful.
What?
Sometimes you need to be very careful about that. I mean, when you turn off the Fi parameter, sometimes there are extra branches.
Right.
Then this localization method will be broken down.
Right. But if you go around it,
Yeah.
then so this is an exact quantity that depends on that, and yet interpolates very nicely between the two.
Yes.
Yes. It's really nice.
So, we were commenting about this regularization for the
Four?
S4.
Yes.
So now it's related to what A and C in central charge.
The logarithmic part of that logarithmic diagonals of four-sphere partition function can be related to A.
Okay, A form. Okay.
A.
Okay.
Yeah.
So that was basically the other half.
There's a
of the
coefficient.
margin.
This is not pointer. Sorry. This one.
Okay.
Yeah. In the four-sphere partition function can be identified as A. And the finite term of four-sphere partition function also has a scalar ambiguity.
Could you go back to the previous slide, actually? Actually, maybe the one before.
One
I
before.
still want to ask you, the one with the scalar, the super curvature.
okay.
So, I'm not confused about the logic here. I thought usually when you couple the supersymmetric theory to this background
Metric.
gravity multiplet, you only turn on some profile. You don't.
Profile means.
Well, I mean, some particular background. You're not. We say only the bosonic degrees of freedom. You only need the bosonic degrees of freedom there. I mean.
What does that mean?
No, you know, you turn on some web for the background, you know, the gravity multiplets, and you only turn on the web for the bosonic field.
Right.
And
Sometimes auxiliary field too.
yeah, the auxiliary fields. And you say, okay, but you say in order to preserve, but you want to demand that the coupling will actually preserve supersymmetry even if all the components of multiplier are turned on. And this discovery of superfields defined using some connection on the superspace. It's some. I mean, what's the definition of R? I mean, you have to start with some connection, some super spin connection.
Definitions of R. I need to look at the paper. Yeah, this is discussed in this paper.
So actually, do we expect this kind of ambiguity only exists for the sphere partition function, or do we expect, for example, in even dimension, if we put out, say, some general Riemann surfaces, then there will still be some, and the same question.
This one doesn't depend on the choice of the curve manifold actually.
Oh, I see.
So I think this finite part always has this scalar ambiguity.
I mean, this whole notion of this curvature is not defined for Riemann surface. Riemann surface doesn't have a metric.
Oh, okay.
Right? So.
No, but the ambiguity comes from integrating square root GR with an arbitrary constant. That's well defined at a Riemann surface,
Right.
and can be given a coupling constant dependent coefficient. So basically, just because of that, because you can add this topological piece to the Riemann surface, you cannot give an unambiguous definition of.
I see.
Right. The finite.
Right.
Other questions? Okay, if not, let's thank Sungjay again.